Section 6.3 is called Separation of Variables and Homogeneous Equations. So there's basically two different components to this section, and we're going to start with the separation of variables. First of all, what do we mean by separable? Well, a separable equation is an equation of the type where we're actually able to separate all the x variables on one side and all the y variables on the other side. In other words, it's the only ones we've done so far, right? This is what we've been doing in the last two sections. We've separated getting all the x's on the left and all the y's, actually we did all the y's on the left and all the x's on the right. Okay, so that's a separable equation. We're able to separate the variables. So we're going to do a few more that are going to be like that. So we haven't done sort of the gamut of things we can do, but we're going to do a few more now. So we're going to find the solution of the differential equation. And this one right here is not exactly written in separated form yet. So what would we need to do first? Divide by some stuff. And if you want to go ahead and not even think about this being written this way, this is a dy dx, right? So tell me what I'm going to be left with on the left. Just the dy eventually, yeah. So what's going to go on the right? Yeah, and where will the dx reside, Abby? Do you know? I mean, yeah, just over here, right? It's not in the denominator, in other words. That's what I wanted to make sure everybody sees, right? Because I've really multiplied by the dx to the other side, but I've divided by the radical. This is separable because we just separated it, right? And that's really what it means. If it's separable, it can be separated. So then we can do the antiderivative. Now, the antiderivative on the left, that's plenty friendly. What is it? Yeah, it's just y. What about on the right? There's a u substitution. Very good. What is the u substitution that we're going to have? Okay, and du? 2x dx. And I don't have a 2, of course, so I'm going to move the 2. All right, so I have on the right-hand side an 11 over 2 that I kind of like to write in front. It's an antiderivative of what? U to the 1/2, and it's negative, yes, du. And I think that, Evan, you were kind of trying to already tell me what the antiderivative was. Is that true? Oh, okay, gotcha. All right, so is everybody good with the rewritten form so far? 11 over 2 integral of u to the negative 1/2 to u. All right, so what's the antiderivative of u to the negative 1/2? U to the positive 1/2, what else? Times 2, because it'd be division by 1/2. Don't forget your plus c, and we've got our y on our left. So what is this equation going to equal? 11 u to the 1/2 plus c. Now, think with me. There are two steps that I need to simplify on this. What do I need to do? Okay, I need to replace u with values of x. What's the other step I need to do? Put the square root back, because it started out in square root form. So this is going to be 11 square root of x squared minus 16 plus c. I just did it both at the same time. Put it back in radical notation and put the u back in. Or put the x's back in for u, technically. Okay, any questions on that? Just more of the same, right? This whole chapter feels like that, just so you know. A lot of more of the same stuffs. All right, the next one, again, we've seen these kind of directions of what does it mean to find a particular solution? Solve for c. It means we're going to do the same antiderivative stuff we've been doing, but in the end, we get to solve for c. Okay, so this one starts to look a little bit different because it doesn't actually start out in, you know, the form that's quite like this. It's similar, but it's kind of a mess. So what would you like to do first to make it less of a mess? Okay, so you want to write the dy dx. Let's start with that. 2x dy dx minus the natural log of x squared equals 0. Now what? Can't pull a dy to the other side directly. There's something I need to do first. I need to add the natural log. Yeah, I got to add the natural log to the other side first. So this is 2x dy dx equals the natural log of x squared. This is actually the first one where we've had to add or subtract. Remember, your goal is to isolate the variables, of course, but you need no, there can't be any addition or subtraction with the dy dx in order to do that. So we move the ln x squared first. Now what? Okay. Okay, so we've got dy over here. Okay, so yeah, like this is what you want me to do. Yeah? Okay. Making sure I heard right. And before I go and integrate, there is one simplification step on the right-hand side that will make your life so much happier. Yeah. Yeah. Bring this 2 down to the front. And you saw that happen on the last exam, didn't you? No, I didn't see it happen. I wish we'd seen it happen. The 2 comes down, right? So we end up with the natural log of x over x. Yeah. So the 2 comes down, cancels with the 2 in the denominator. I end up with ln x over x dx. I am going to integrate, and as I integrate, I notice that I do not have a closed form integral for natural log of x. I don't. You have tables, and it's in the tables. Don't get me wrong, it's there. But you don't need it, because you actually have the ability to do u substitution here just fine. Your u would be the natural log of x, because what's du then? 1 over x dx, which is exactly the other piece of this, right? Right there. So on the left-hand side, I have y. On the right-hand side, I have the integral of u du. How are we doing? It'd be good to ask if you're lost. Okie dokie. What's the antiderivative of u? Okay, u squared over 2, or 1/2 u squared, and then I need a plus c. U is not really my variable. My variable is supposed to be an x. So this is really supposed to be 1/2 natural log of x squared plus c. Right? Am I done? No, what's wrong? Yeah, this was a particular solution. I have a y of 1 equals to 2, right? I can find c. So if I put in y is 2 and x is 1, I need to solve for c. What is the natural log of 1? 0. It's very friendly. Which means that I'm left with 2 on the left and c on the right. So c is simply 2. So my particular solution is y equals 1/2 natural log of x squared plus 2. Oh, I said 2 and then I wrote c. Yes, it is 2. Thank you. Thank you. Okay. A variation on directions. We saw this last time too. This direction, or this form of a direction. It says find an equation of the graph that passes through the point and has the given slope. Sounds like we're doing something different, right? But we're not. We're finding an equation whose derivative looks like this. And it has the particular point that it goes through. This is the exact same problem we just did. Just set up a little bit differently in terms of its language. So starting with this, I have dy dx equals y over 2x. Now what? Okay, multiply by the dx. Okay, so we're going to divide by y to get 1 over y on the left, and we're going to multiply by the dx to get so now we have 1 over 2x on the right, and we have dx on the right. So in some sense, I multiplied by 1 over y, and I multiplied by dx. Is everybody good with that? So I do, in fact, now have all the x's on one side and all the y's on one side. And I can now find the antiderivative because I've separated them. Hence, it's separable. What's the antiderivative on the left? Natural log absolute value y. What's the antiderivative on the right? Natural log absolute value 2x. Oh, yeah, we could do it that way. I was going to do it differently, but yeah, we can definitely do that. So do it like this. Okay, we'll see what you think about that in a minute. I'm not sure that's the easier choice, but we'll see. That's actually what I have written down in my notes, to be honest. This will work. Okay, now what? Goal is to solve for y. Okay, it gives me y on the left. What's going to happen on the right? Let me see what I did. Oh, I know what I did in my notes. Now we do have issues. What are we going to do about those issues? I mean, obviously the e to the c, well, I'll call it c1 here, it can just be c, right? But what about this fact that I've got e to the 1/2 natural log of x, and we know that e and natural log are inverses, but somehow there's a 1/2 that's messing with things. We need to bring it up, yes. This is an exponent. So this is essentially e to the natural log of the square root of x. Are you with me? Now I'm not done, but I'm sort of just pausing intermediate here to remind you. Right? The 1/2 in front, and then what? The absolute values don't end up mattering. Yeah, because we got the square root. Yeah, exactly. So what happens when I have the e to the natural log of the square root of x now? Do you know? Yeah, that's the square root of x. So this is y equals c square root x. So it actually does clean up pretty nicely. But we're not quite done because the whole point was that we have a point given. And that point that's given allows us to find c. So y is 1, x is 9. What's c? 1/3. Square root of 9 is 3. We'll divide the 3 to the other side. c is 1/3. So my particular solution is y equals 1/3 square root of x. Okay, so what I hope you feel like from the first 3 examples is, okay, but that wasn't anything I didn't already do. And it really wasn't. I mean, we solved a little bit of a different variation of it right here. We didn't see square roots coming into play before. Okay, fine, it's just a variation. But it didn't do anything any differently, right? I mean, we've been doing separable functions the whole time. Okay, but the next part is different. Okay? So the other part of these directions talk about homogeneous functions. So a function that is not separable in x and y can be made to be separable with a change of variables. At least, I mean, this is the definition of a homogeneous function. It's one that can be made to be separable with a change of variables. The change of variables is of the form f of tx ty equals t to the n f of xy. And a homogeneous differential equation is one of the form m of xy dx plus n of xy dy equals 0, where m and n are homogeneous functions of the same degree. Okay, so show of hands, who feels like you just read Greek? Just a little Greek there, right? Just a little Greek. Yeah. Okay, so we're going to break it down, of course, into a couple of steps of how these problems work out. the first thing we're going to verify is that we're going to show how you decide if something's homogeneous. Because there's two directions here. One that's talking about what it means to be homogeneous, and the other one that's talking about what it means to be a homogeneous differential equation, right? So our first question that we're going to look at is how we determine if something is in fact homogeneous. Okay, did everybody get all these details written in? We're ready for the next one? Okay. So to determine if the function is homogeneous, and if it is, determine its degree. So let's go back over here and see what it said to be different, or to be homogeneous. Right here, it says that in order to be homogeneous, if I were to replace x with tx, and I were to replace y with ty, somehow I'm going to be able to factor those t's out in front and have the same function I had to start with otherwise. So that's what we're going to try. We're going to take this function, and we're going to replace the x's with tx, and we're going to replace the y's with ty. And you're going to be super careful as you do it so that you don't end up making your t's look like pluses. So this is tx, ty, over the square root of tx squared plus ty squared. So some of you have neater handwriting than others, and you know who you are. Be neat and careful on writing these out, because you're going to lose something along the way and you're going to think it isn't and it is and it is, or it is and it isn't, okay? Be careful. On the top, if I were to clean this up, our goal is to get something that looks like this with t's in front of it, okay? So on the top, that seems pretty reasonable. What would I change the numerator to get it into the form where it looks like the original part with t's in the front? Yeah, I'd not pull a t out exactly. I think you're thinking about it like I'm factoring, and it's not factoring. Because it's not addition or subtraction, Abby. That's why it's not factoring. We can't divide by t unless we divide both sides, and I don't want to manipulate the left-hand side. I need it to stay f of tx ty. Say that louder, Evan. Yeah, we're still not pulling it out, but we're just simplifying the numerator where we collect the t's at the beginning and we write the other pieces at the end. Okay, does everybody agree that that is the same as the numerator I already have? Okay, so I'm not changing the function, I'm just collecting things in a way that's going to make it more convenient. Okay? Now in the denominator, again, let's just clean it up for the first step. What will it look like if I clean up the denominator? T squared x squared plus t squared y squared. Exactly. And now the language that you guys keep using is actually truly appropriate here. I can pull out a t squared because it's in both terms, and that's factoring. All right, so I've still got a square root here, but I've got t squared in front, and I've got the x squared plus y squared after it. Okay, is everybody okay so far? A lot of algebraic manipulations, what really we're doing. Now I have underneath a radical a t squared and an x squared plus y squared. Some of that simplifies and some of it doesn't. So tell me what the denominator will in fact simplify to if I do it appropriately. Okay, so my numerator stays the same. Let me rewrite that. The square root of the t squared is okay, and that's t. But I cannot take the square root of the x squared plus y squared. Why not? Because there's addition underneath there. So it's okay to separate out the multiplication here, right? It's okay for me to write this as t squared to t squared and this as square root of x squared plus y squared, because the t squared is multiplied by the x squared plus y squared. But it can't separate out the addition itself. It's actually just not, it's not a true fact that the square root of x squared plus y squared is x plus y. It would be wonderful if it worked that way in terms of, you know, logistics of solving it and things. It doesn't. It's just not a true fact. So if I simplify this now, what do you see from the numerator to the denominator? There's a t that cancels. So in the numerator, I'm left with a t, but in the denominator, there is no more t. And in particular, if you notice, your denominator looks exactly like it did in the original function you were given. And the numerator does too, except for the t. This now has the form of t times the original function f of xy. So it is homogeneous because you had the ability to change it so that the t's were pulled out in front and you still had the f of xy that you were originally given separated from it. The other question the direction asked then was to do what? The degree. And it's 1. Its question is asking you what is the number up here, what is the exponent on t? And in this one it's 1 because we don't have anything written, so it's an understood 1. So this is homogeneous. Of degree 1. Okay, so that's how we determine if something's homogeneous. The other part of the definitions that I gave you told you what you would do in order to separate or able to use a homogeneous differential equation. Okay? So, we're talking about change of variable next. So if capital M of xy dx plus capital N of xy dy equals 0 is homogeneous, so if it has this form, then it can be transformed into a separable differential equation by the substitution of y equals vx. This is the tx we saw in the previous problem, right? Or the tx we saw in the previous working out of the previous problem, where v is a differentiable function of x. Okay, here is your word to the wise. I think we have time for our last example. It's a long example, and you need to write small. This is my page. Okay? We got a lot of notes to write in here. Write small. All right? So let's see how this works. Did everybody get all these? Okay, sorry, Nathaniel. Okay, are we good? This says to solve the homogeneous differential equation. It tells you it's homogeneous. It didn't ask you to figure out if it was. Did you see that? So that's actually very nice. However, in order for it to be able to be worked with, we have to be able to do some changes of variables and to do some separation. That's the whole point. So taking a look at what we have, let's first make it not have a denominator. Are you guys good with that? So I would do that by simply multiplying by the 2xy. And then I'm not going to write dy. I'm not going to write y prime. I'm going to write dy dx. And it equals x squared plus y squared. I'm going to do what I would do on the other problems as well. I'm going to try and move it so that I have dy on one side and dx on the other. So this is now 2xy dy equals x squared plus y squared. I'm going to put that in parentheses because that is multiplied now by dx. And can you see right away that this is definitely not separable? There's no way to move all the x's to the right and all the y's to the left using the tools we've done so far anyway. It's just not possible. Okay, so at this point in the problem is when we decide we're going to make this substitution step that we talked about over here. The substitution is that y is equal to vx. Okay, so we have y equal vx. But anytime we do a substitution, I have to actually figure out what the dy is because that's part of the substituting step, right? There's a dy in my problem as well. What is dy? That's part of it. The plus c's come into play with antiderivatives. What did it identify that v is? What did it say v is? And the key word I want you to see, actually bigger than that, is that it is a function of x. V times x is a product. Right? V is like sine of x. If you had sine of x times x and you try to take a derivative, you have to do a product rule, right? Or it's a square root of x squared plus 3 or something. Well, yeah, it's a variable. It's not a constant. Everything we've done so far in the last section, we had k's and c's and they were all constants and we can just sort of ignore them, right? This is not a constant. It's a function. So we have a product rule. So part of it was what exactly was said by Nate. This is v dx plus x dv. That's right. And we have the substitution that we're going to make to eliminate all my y's. So what seemed like it was a fun substitution is all of a sudden now even more fun, right? I've got 2x and y is vx. But dy is x dv, whoops, plus v dx. On the right-hand side, I have quantity x squared plus vx quantity squared and then dx. This is messy, right? Yeah, I mean like really messy, not just like sort of kind of, like it's a mess. And it's really easy to lose stuff, so be extremely careful as you're working your way through. Okay, on the first piece, right here, I can combine these pretty nicely to say 2x squared v. I'll need to distribute that through in a moment, the x dv plus v dx, right? Over here on the right, I'm going to go ahead and distribute the dx through. So this is x squared dx plus v squared x squared dx. Are you guys okay with that so far? I need to do the same thing on the right-hand side by distributing. So I need 2x squared v times x dv, which will give me what? It'll actually be 2x cubed v dv. Oh, did you write yours the other direction?
When you wrote VDX, I did the opposite.
Okay. And then the other one would be 2x squared v squared dx. Did we get the pieces even if they're in a different order? Does everybody have those pieces? Okay, now the whole point in doing this mess is to be able to separate the variables, and now I have variables v and x, correct? So my goal is the same as the goal before. I need to have all of one variable on the left and all of the other variable on the right. Now in particular, I do also need to be aware that in order to do that, I need to get all of the dx's together and all of the dy's together, right? I don't mean dy's, dv's together. So at the moment, I only have the dv on the left, correct? So the piece that's on the left that has the dx in it, I'm going to move it to the right. So on the left, all I now will have is 2x cubed v dv. And on the right, I have x cubed dx, I'm sorry, x squared dx, plus v squared x cubed dx. And now I have minus 2x squared v squared dx. Did I get all those in there correctly? I think so. Maybe not. Oh man, I definitely turned something into a cube that wasn't. This is what happens, and I don't even have messy handwriting. That was a squared. X squared dx, v squared x squared dx, minus 2x squared v squared dx. Okay. Two of the pieces on the right are identical, at least common enough that you can completely work with them. Well, we can't eliminate it exactly. We'll clean it up in here in a second. But do you see that both of these are the same? We can combine those, right? Anytime we can eliminate a term by combining it, that's a good thing. How do those combine? What do I get? Yeah, negative v squared x squared or x squared v squared if you prefer dx. Now, truth be told, that's way better than it was, isn't it? Yeah, this is a considerable improvement so far. Let me move this to the next screen. Okay, on the right-hand side, what do you think might be a helpful step? Pulling out the dx, I agree. So this would be x squared minus v squared x squared dx. I think it might be helpful to plot the x squared as well. Would you guys be okay with me doing that?
Yeah.
Let me redo that step and do that. X squared and then 1 minus v squared dx. Say a little bit louder, Nathan, or Nathaniel, what you had said before about the x squareds. Or was it Evan? I'm sorry. Okay, well, how can I do that? Why? Yeah, so we could just divide both sides by x squared in essence because there's an x cubed on the left and there's an x squared on the right. Does everybody see that okay? So you're right, we can do that. So I've got 2, well, let me write it in just so that everybody sees that I did it. So this piece eliminates, and this piece eliminates with 2 of those, so it leaves me with 1. So I have 2xv dv on the left, and I have 1 minus v squared dx on the right. Now what? I mean, it's considerably cleaner. Can I do the antiderivative? Not yet. Why not? Yeah, I need the variables on the same side. In particular, I need to move the x to the right and the 1 minus v squared to the left. So this is going to be 2v over 1 minus v squared on the left. And this over here on the right is going to be 1 over x dx. And now what? Okay, so if I put the antiderivative notation in now, the right-hand side's easy enough. It's just natural log absolute value x plus c. And there's a u substitution now on the left, right? We did a y substitution before, or v substitution before. Now we're doing a u substitution. So this is u equal to 1 minus v squared. So du is equal to negative 2v dv. I'm running out of space. So I have everything I need except for the negative. Agreed? So I have negative integral of 1 over u du. What's the antiderivative of negative 1 over u? Negative natural log of the absolute value of u. So I got natural logs everywhere now. Now, truth be told, I've got a couple of substitutions that I got to go back through, but I found the antiderivative, which was the whole goal, right? I mean, really, the goal was separate the thing and find the antiderivative. So I've done the calculus. Now you got messy algebra again. Messy algebra on the front end, messy algebra on the back end. Okay? So as we're looking at this messy algebra, I have the negative natural log of u, but u was 1 minus v squared. Equals the natural log of absolute value of x plus c, but what is v? It is y over x. Back on the previous screen, v was, what did I write it as? Y was vx, so v is y over x, which is now what I have there. Good. And this equals the natural log of the absolute value of x plus c. And they're c1s because we're going to change them into c's later. All right. Now, at some point here, I've got to get common denominators inside of that absolute value on the left, and I'm going to have to take that negative as an exponent now, because I've got I could avoid it on the last problem, because I could just distribute it to the other side, right, divide it to the other side, but dividing it to the other side on this problem is not especially helpful, because I got natural logs on both sides anyway. At some point, I'm going to have to make it the exponent. So if I clean this up, let's work this really, I know we're running out of time, I told you it's a long problem. If I multiply and distribute, this will end up giving me x squared over x. This is x squared minus y squared over x squared. There's a negative in front. Equals the natural log absolute value of x plus c1. This negative brought to the exponent will flip my fraction upside down. So this is the natural log now of the absolute value of x squared over x squared minus y squared. And that's actually quite friendly, because now I'm actually able to use the exponential notation, right? Because I've got the natural log there, I can put e's on both sides. So on the left, I end up with x squared over x squared minus y squared. And on the right, I end up with a c times, is it x? Yeah. C times the absolute value of x. Or c times x. We'll leave the absolute values for the moment. The goal is to solve for, I don't even know, what did it say? Solve the homogeneous differential equation. I don't think, well, maybe we can solve this one for y. What I have in my notes is that I've solved it for c, which is interesting. Not sure why I would have solved it for c. Oh, because y is squared. We're going to end up with a square root if we get involved in that. Notice that we do have an x on the right and we have an x squared on the left. This does simplify if we multiply by 1 over x. So I end up with an x on the left and then x squared minus y squared on the bottom of that, and then this is equal to c. Because x squared and y squared are involved, but the x on top is actually still a single x, it doesn't have a power of 2, the absolute values are still there. So if you think about it, I'm actually multiplying by the absolute values on these, is what I'm doing. There's not any better form to write this in, because I know I can't solve for y, right? Because I would have a square root and a plus or minus in there, so this is an acceptable form in which to leave it.